So let's close out the discussions from David Neelan's book with this podcast by making a few more points. So here are the CMIP 6 annual global average temperatures with the base period over the period 1850 to 2100. So here is the historic climate change looked at in terms of global average near surface air temperatures. We have been typically looking at anomalies with respect to some base period, but here we are looking at total temperatures. It doesn't matter. You can still see the warming and the acceleration of the warming in the recent decades. And here we are looking at future projections from the combination of SSPs and RCPs. So the historical period versus SSP1 2.6, so sustainability with low emissions, SSP2 which was something versus middle of the range emissions, and business as usual with destructive human behavior. So you can see the range. We are going to end up about 5 degrees C warmer than the global average temperature of around 15 degrees centigrade. We have now around 20 or so. With a large range in terms of model simulations. So this model difference is critical as well, and you have to decide how to depict the range of models and the mean for policymakers, because easily one can argue that the models are very different, which means the information is not reliable. So then that can be used in all sorts of funny ways and not so intelligent ways, or dangerous ways of what to do with the future of climate, and how to invest, how much to invest, and so on and so forth. And there are others down here. So you can see that SSP 1 2.6 should keep us within 2 degrees. So from the level of here, it doesn't go beyond 2 degrees. And already there is discussion that we are not on target to meet 2.6 right now at all. So that may require revising the nationally determined contributions under Paris Agreement, which has already started, with many countries having submitted revised plans. Also now there is emphasis on net zero. Who will get there, whether everybody will get there, how they will get there, and all are details that are not so easy to push under the rug. So we have to watch out how these will evolve over time. So another way to look at it is again as anomalies. So global surface temperature increase since 1850 to 1900, baseline as a function of cumulative CO2 emissions. And probably many of you heard that people saying the UN Secretary General did that, and then Greta Thunberg did that, and many people, maybe Leonardo DiCaprio is doing, saying we only have 10 years to save ourselves from the end of the world, which are not completely agreed upon in terms of a narrative for the future by everybody, especially many scientists. What is that story? Basically, you can see that there is a nearly linear relationship between warming and cumulative CO2, and that is used to say that to reach a 2 degrees C warming, we can only emit so much CO2, and we are emitting at this particular rate right now, which means we only have so many years left. This is not a very good idea, because there are many uncertainties in those carbon cycle calculations, and how the carbon cycle will respond in the future with all the internal feedbacks, and how human activities and population growth and renewables and so on will affect things in the coming decades. So generally saying something catastrophic will happen after a certain period is not a good idea, because already many climate change impacts are happening and nothing dramatic may happen. For example, if you exceed the 2 degrees C target, as soon as it's exceeded, newspapers will be blaring, media will be shouting, saying we crossed 2 degrees C. But what if it comes back next year? how long does it have to stay above 2 degrees centigrade for impacts to have catastrophic outcomes, and so on. So too many uncertainties, so don't buy into this idea of how many years we have left for saving ourselves. Okay, keeping that in mind, and that's my personal opinion, but there are many articles written on this as well by Mike Hulme and others. Okay, so the linear relationship between the cumulative CO2 emissions and the global warming for 5 illustrative scenarios until 2050. Okay, so SSP 1.5, 2.6, 4.5, 8.5. So you can see how the cumulative CO2 increase leads to larger and larger warming. At any time we can stop emitting and that will reduce the warming, and any additional gigaton you put in is going to add to the warming, so that has to be kept in mind as well, which means saying that we have already committed to some warming can be misleading as well, because adding more carbon will do additional damage. So looking here at the projections, future cumulative CO2 emissions differ across scenarios and determine how much warming we will experience. So here we are in terms of the cumulative CO2. So SSP 1.9 is here at 3,000 gigatons, so 3 trillion. Across scenarios, SSP 1 2.6, SSP 2 4.5, and SSP 8.5, which is basically the business as usual scenarios where we don't do anything. So those have to be kept in mind. Coming to the model differences, we're looking here at GFDL CM 2.40, NCAR CCSM 3, and MPI ECM 5 for the same period 2040 to 2069, and you can see that there are significantly different projections in terms of polar amplification, in terms of pattern of tropical warming, ocean warming, and so on. Especially some critical regions, it matters how much you warm in the east versus west, because there is a strong feedback between the sea surface temperature gradient, the pressure gradient, the winds, ocean heat uptake, and so on. The whole discussion about the so-called global warming pause is related to how the East Pacific will warm with respect to the West Pacific, and how the east-west sea surface temperature gradient, pressure gradient, and winds will change with global warming, and so on and so forth. So annual average change in surface air temperature relative to 1961 to 1990 from 3 climate models for a 30-year average centered on 2055 from simulations with greenhouse gases and sulfate aerosol forcing. So keep in mind that when you have such different outcomes based on the same scenarios, it can be used to make arguments that climate models are not useful, so one has to be careful about interpreting the differences and understanding why there are differences. Of course, the problem is bigger when you look at precipitation. So for the same period, same model, GFDL CM 2.0, CCSM 3, and ECM 5, you can see that the precipitation change for June to August for the same base period are also remarkably different, and such large change differences in heat sources, because this amount of rain is a heat source which affects global climate and global weather, and also depends on whether this rain is coming as extreme events, heavy rain events, steady rain, and so on and so forth. And you can see that this one makes India very dry, this one makes it wet, this one makes it less almost neutral, and so on. So these are not small differences, so one has to be very careful about those. And here is the DJF precipitation change again. Precipitation change for a multi-model ensemble average for 2070 to 2099 for December, January, February, and June, July, August for simulations with SRES A2, GHG, and sulfate aerosols. This is an older simulation, but the story remains almost the same, in the sense that models still have significant differences, but there are ways to deal with the differences, and there are ways to understand the differences. And the idea is not always to drive all the models to produce the same answer, because consensus answer is not necessarily the same, but to understand why the differences exist and what they mean in terms of the reliability and skill and impacts of internal feedbacks, their climate sensitivities, and so on and so forth. So this is just a little on extreme events, on how global warming shifts the tails, the cold tails to warmer tails, and warm tails to warmer tails. So these are very critical. Extreme events are already found to have increased across the globe, especially in things like the hurricanes, cyclones, and monsoons, for example, and even sea levels, heat waves in the ocean, heat waves on land, and so on and so forth. Finally, schematic summary of the best estimate of climate changes due to greenhouse warming, northern hemisphere, northern and southern hemispheres. So this is an older one, but basically troposphere warming, stratosphere not much change. This is the land nighttime air temperatures rising faster than daytime temperatures. Mid-latitude soil moisture increases in winter and decreases in summer. That's what warming does. And here possible changes in ENSO SST variability. Again, uncertainties there in terms of ENSO amplitude, frequency, and duration. Models don't necessarily agree. Near surface air temperature increases greater at NH high latitude, so polar amplification is stronger in the northern hemisphere winter. Sea level rise, near surface ocean temperature increases, but less in the North Atlantic and Southern oceans. That is already observed. Deep ocean is warming slightly, already observed. Tropical East Pacific warms more than tropical West Pacific. This is still controversial because in the first 2 decades of the 21st century, tropical East Pacific has warmed less actually, and the ENSO pattern has changed as well. Sea ice, northern hemisphere below average, southern hemisphere average or slightly below. Water vapor increases, very clear. Tropical precipitation variability increases, already observed. High latitude precipitation increases year round in northern hemisphere. Please check that. Mid to high latitude precipitation increases in northern hemisphere. Excuse me. Excuse me. Okay. Evaporation in the tropics increases, and I already read this. So, sad to end the podcast like that, but my throat dried up all of a sudden, so I'll stop here.